All right, so let's tackle another linear momentum problem. So let's read the problem first. A ballistic pendulum, as shown in the figure, was a device used in the past century to measure the speed of bullets. The pendulum consists of a large block of wood suspended from long wires. Initially, the pendulum is at rest. The bullet strikes the block horizontally and remains stuck in it. The impact of the bullet puts the block in motion, causing it to swing upward at a height h. If the bullet has a mass of 6.28 grams and the block has a mass of 2.8 kilograms, swings up to a height of 21 centimeters, what was the speed of the bullet before impact? Now, the fact that they're stuck together after the impact means that it is a completely inelastic collision. So, we want to know the speed of the bullet before impact. Now, let's analyze this. At the beginning, all the energy was put into the bullet. It was all kinetic energy. And then as it went up, it was converted to potential energy as it went up into the ballistic pendulum, and the ballistic pendulum got a height of 21 centimeters. Now, this means that we can find the change in kinetic energy. So let's first off calculate the final potential energy. So it would be UG final, and that would be MGH. Let me just make that bigger. And that's equal to 2.8. Now, the mass is the total mass because they got stuck together. So that would be 2.8. So 6.8 grams is 1,000. So plus 2.8. That will be 2.8068. So that will be 2.8068 kilograms times 9.8 times, and then 21 centimeters. We have to convert that to meters. So that would be 0.21 meters. And that will give us 0.21, that would give us 5.78. 5.78 joules. Now, right after the impact happened, all of the kinetic energy was transferred. So all the energy was transferred, and it was transferred to the ballistic pendulum. So the kinetic energy right after the impact was equal to 5.78 joules right after the impact of the ballistic pendulum and the bullet. So not just the bullet. So when right after they impacted that's the same energy that was used right after the impact. So there was no energy loss there. So we can use conservation of energy theorem. Energy initial is equal to energy final, and energy initial, it was all at the beginning kinetic energy, so 1/2 mvi squared is equal to 5.78 joules. Now let's convert that. So 1/2 m mass is 2.8068 times vi squared, which is what we're going to find, 5.78 joules. Now, so let's multiply that. 1/2 times 2.8068. So that is 1.4034 times vi squared is equal to 5.78 joules. Now let's just divide 4 and square root. So vi right after the impact is equal to 2.03 meters per second. Now we'll use this for the we're trying to find the initial like really before the impact happened of the speed of the bullet. Now why we need this is to use the conservation of momentum. So if we use conservation of momentum, so this is momentum before impact, and that's after. Just to be clear, And before impact, it's just equal to the mass of the bullet, because the bullet is alone, so let me just bullet, times the initial speed which we want to find. And that's going to be equal to, at the end, the total mass times 2.03 meters per second. So let's really get all these variables that we have. So 6.8 in kilograms is 0.0068. So 0.0068. Oops. 68 kilos times VI is equal to MT. Total mass was 2.8068. So 2.8068 times 2.03 meters per second. So let's simplify times 2.03 and divide 0.068, and that gives us that the initial speed of the bullet was of 837.91 meters per second, and that's the final answer. So if you guys like this video, then give it a like. If you want more videos like this, then make sure to subscribe. And yeah,